Alright, this is number 6 from the 2011 AP Physics B exam, and this is a modern physics problem, primarily dealing with exciting the atom. And so we have the following energy levels of a hypothetical atom: negative 6 eV, 3 eV, and 1 eV. And we need to draw the energy level diagram and then label each appropriately along with a quantum number. This one is as simple as it sounds, as long as you understand the energy level diagram business. You're going to have your energy on one axis. Go ahead and label that. You're going to have your quanta listed as individual lines, your quantum number. So this would be your ground state, n equals 1, n equals 2, and then n equals 3. Then I think the challenge is to determine the correct order. And remember, the negative means that's how much energy would be required to cause the electron to be ejected from this atom. So that's going to be the bottom number. So we have negative 6 eV here, negative 3 eV, and then negative 1 eV. Alright, B. Calculate the wavelengths associated with each possible transition between the energy levels. Now, we're talking about each possible transition between the energy levels. So we're going to have 3 different possible photons. Now, I encourage you not to draw on this once it's created. I'm going to draw on it for the sake of explanation. We could have an electron that's going to fall from n equals 3 all the way down to n equals 1. You could have an electron, and that'll emit a high energy photon, by the way. You could have an electron go from energy level 3 to energy level 2, emitting a low energy photon, and then energy level 2 to energy level 1, emitting another low energy photon. So these are the 3 possible photons. Again, I wouldn't draw on yours. The wavelengths associated are going to be associated with the energy exchange. So I think the easiest is to just simply say, energy of the first photon, or a lot of times you see the notation n equals 1 to n equals 3, or n equals 3 to n equals 1, I guess would probably be the most appropriate. Yeah, let's do that because we're falling from 3 to 1. I don't believe this is a required step, but it is helpful to label which energy you're dealing with in some capacity. So I'm looking at the energy as we fall from 3 to 1. I'm going to use hc over lambda. Lambda is what I'm looking for, and hc is a constant, and I have that constant in eV, so that's what I want. So I'm going to say the wavelength that comes from the 3 to 1 transition is going to equal hc over the energy 3 to 1. hc, we're going to use the hc that is in electron volts, so 1240, and that's going to be eV nanometers. And then we're going to divide that by the energy exchange from 1 to 6, which is 5 eV. Your EVs cancel out. That means it's going to leave our wavelength in nanometers, which is perfectly appropriate. And we're going to get 248 nanometers. That's going to be the first. We have to do this 2 more times. Now, it also is important to kind of get an idea of relative wavelengths. So as you go ahead in the other ones as a kind of a math check, this should be my shortest wavelength because it's my greatest energy. And remember, wavelength is inversely related to energy. So if we have a high amount of energy, we should have a low wavelength. So my other 2 photons should be larger than this. I'll now go and do the energy associated with, I don't know, we'll say from level 2 to level 1. So I'll go ahead and label this E21 equals hc over lambda 21. And so that lambda that I'm looking for is hc over that E. Once again, it's just going to be plugging in. We're going to use 1240 up top. And we're then going to use the association between 2 to 1, which is 3 eV. And we're going to go ahead and grab a 413 nanometer wave or particle. Or wave or particle, I don't know. Anyhow, and then we're going to go ahead and do one more. We're going to have the transition from n equals 3 to n equals 2. I'm just going to get to the bottom line. Lambda 32 is going to equal hc over E32. It's the 1240. And the transition between 3 to 2 is only 2 eV. And this is 620 nanometers. These are the three different particles that are associated, or that are ejected. The green one and the red one are in the visible light spectrum, and this blue one is probably the ultraviolet. So when I say green and red, I mean green and red ink. Those are not necessarily the wavelengths associated with those colors, although red is close to that. Green is not. Alright, C. Atom is in the ground state. When an electron traveling with a speed collides with it, we want to know if it can excite the atom to n equals 2 state. Now, most often not, at least in my classes when I teach it, I talk about a photon coming in and hitting an electron and seeing if that electron will absorb that photon to get to the next level. This is actually an electron coming in, and electrons can collide with electrons just as well. So this is, don't let that part trip you up. Electrons can excite other electrons. We just need to figure out if it has enough energy first. So there's multiple ways of doing this. Perhaps first figure out the n equals 2, or the n equals 1 to n equals 2 requirements. So we're going to need 3 electron volts to excite to the n equals 2 level. So now let's figure out how many electron volts the energy of the electron is if it has that much speed. And remember, this is kinetic energy, so the kinetic energy of the electron is 1/2 mv squared. Right, we're going to use the mass of the electron, 9.11 by 10 to the negative 31 kilograms, and 1.3 by 10 to the 6 meters per second. And don't forget to square that term. And we're going to get 7.7 by 10 to the negative 19 joules. Don't forget that's a standard unit. We're using standard units in this equation, so we're going to get standard units of joules. We're now going to divide this by the conversion to electron volts of 1.6 times 10 to the negative 19, and we're going to get 4.8 eV. Now here's where I caution you. Here's where it's going to get a little confusing, or maybe not. Typically you're taught that the amount of energy that the electron needs to absorb needs to be exactly equal to the amount to get to that level. So 3 eV or 5 eV. And so you might think 4.8 eV won't do anything. But this is only true if it's a photon, because that photon gets completely absorbed by the electron. So if it's not the exact amount, it won't be absorbed and it'll just move along. But this isn't a photon in this example. This is an electron coming in. It does not have discrete energy packets associated with it. It is continuous energy. It is able to change in speed, not on its own, but if its speed was lower than this, it can have any range between 0 and 4.8 eV without any stepping involved, any discrete values necessary. So when an electron comes in and hits an electron, if it has at least the amount of energy required, then the electron that it wants to hit will absorb the exact amount needed, so it'll take that 3 eV, and then this other electron will continue minus that 3 eV, so it'll go slower. So there's no discrete energy values necessary, no quantum values necessary when it's bits of matter hitting bits of matter. It has to deal with those energy packets that are associated with photons. So the answer to this one is yes, it can. And you do need to explain it. You should justify with the math first, and then explain that 3 electron volts will be exchanged to the electron in the ground state to excite it to the second energy level. Alright, in D, another electron excites the atom from the ground state to the n equals 2 state. The atom then decays back to the ground state by emitting a photon. So now we're this purple, let me move this math over out of the way. So I want to come back to this in a bit, so I'm going to leave this off to the side. But this guy is now falling back to energy level 1. And ultimately, we want to know the amount of energy associated with that fall in joules, and then we want to determine where in the spectrum that is. Well, the energy in joules should be pretty easy to figure out. If it goes from level, excuse me, from level 2 to level 1, it's going to release 3 electron volts. So the energy that we're looking at is 3 electron volts. Well, 1 electron volt is 1.6 by 10 to the negative 19 joules. So we're just going to multiply these two numbers, and we're going to get the 4.8 times 10 to the negative 19 joules. And that's the answer to D1. Now D2 wants us to determine where in the spectrum it is, and if we can't determine it, we're going to put that down. But we can, because we know the energy associated with 2 to 1 also associates with a photon of 413 nanometer wavelength, and that is within the visible light spectrum. Let's give you the blue-violet end. You should know that that 400 to 700 nanometer region is the visible light spectrum. Anything shorter or longer than that is outside the visible light spectrum. Alright, that is it for number 6.